Okay, now just for some further harder examples now. So just using the same ideas. Use a right angle triangle this time within a quadrant diagram to help find the exact value of the following. So we're looking at, we're trying to find sine to the minus 1 of sine to the minus 1 of cos, I've written it all wrong. We'll start again. First question, the sine of cos to the minus 1 of 3/5. Okay, right, we'll start with that one. Okay, so let's just let alpha equal cos to the minus 1 of 3/5, and we'll draw that diagram. So remember, this is a right angle. So if alpha is cos to the minus 1 of 3/5, therefore cos of alpha is 3/5. So here's alpha, cos of alpha is 3/5. This is clearly a 3, 4, 5 Pythagorean triad, so this other side over here is 4. Okay, so therefore, remember we're trying to solve sine of cos to the minus 1 of 3/5. We've let alpha equal cos to the minus 1 of 3/5. So therefore, we're trying to find, so sine cos to the minus 1 of 3/5 is the same as really finding sine of alpha. Now the sine of alpha, because remember, alpha is cos to the minus 1 of 3/5, because we've let alpha equal that. So we've just labelled this as alpha, so therefore the sine of alpha in this triangle is 4/5. It's going to get Pythagorean triad, so with this one, find the cos of sine to the minus 1 of 2/3. Let alpha equal sine to the minus 1 of 2/3, therefore sine of alpha is 2/3. Again, drawing a right angle triangle, sine is opposite over hypotenuse, therefore the adjacent side here would be the square root of 3 squared minus 2 squared, which is the square root of 9 minus 4 is the square root of 5. So trying to find the cos of the inverse sine of sine to the minus 1 of 2/3 is the same as finding cos of alpha, because we've defined alpha as sine to the minus 1 2/3, and cos of alpha is root 5 on 3. Now, I'm just going to do another one, but we're going to have a negative this time, okay? So we want, want you to find the cos of tan to the minus 1 of negative 1/3. So we're going to let alpha equal tan to the minus 1 of negative 1/3, which means that the tan of alpha is negative 1/3. Now, we've got to work out which quadrant we're going to be in. So tan is negative in quadrants 2 and 4, but remembering that the range for inverse tan is from negative pi and 2 to pi and 2, so we have to go in quadrant 4. So I'm going to draw my quadrant 4 thing like this, but it doesn't matter if I don't put it in that orientation, okay? Remember, if that's your axes, right? Tan is opposite over, so the negative 1 would be there basically, and the 3 is there. So what we're going to do, we know that we're in quadrant 4, so when we do the cos of whatever we've got here, we've just got to remember that we're in that we're going to be in quadrant 4. So this distance here, this is a length of 1, but it is going down. The reason we've got negative 1/3 is that we're in quadrant 4, and this is a negative. This is negative 1 going down, but the distance is actually 1. So the hypotenuse is the square root of 3 squared plus 1 squared, which is the square root of 10. Okay, so by finding cos of tan to the minus 1 of negative 1/3, that's the same as finding the cos of alpha, okay, which is cos of alpha is 3 over root 10. Now, is positive because we know that cos in quadrant 4, see we're in quadrant 4 here, that cos is positive in quadrant 4. So this is 3 over root 10, and if you want to rationalize it, it would be 3 root 10 over 10 by multiplying numerator and denominator by root 10 on root 10, okay? So finding the tan of cos to the minus 1 of negative 3/4, again we're going to let alpha equal cos to the minus 1 of negative 3/4, which means that the cos of alpha equals -3/4. Now, we've got to work out what quadrant we're in. Now, cos is positive in quadrants 1 and 4, so it has to be quadrant 2, okay? Now, is this allowed with an inverse cos function? Yes, it is, because if I draw the inverse cos function, it looks like that. And the y values go from 0 to pi, so which is 0 to 180 degrees. So yes, quadrant 2 fits in. So we've got cos of alpha is 3/4. And the reason it's negative is that you've got the -3 there. And to work out this side here, it would be the square root of 4 squared minus 3 squared. Remember, this is just a distance. So when I'm working out these distances, we don't worry that that's -3 along here, but the distance is 3 units, okay? So square root of 4 squared minus 3 squared, that's square root of 16 minus 9 is the square root of 7, okay? So therefore, remember we're trying to find tan of cos to the -1 of -3/4. That's like finding tan of alpha, because alpha equals cos to the -1 of -3/4. But remembering we're in quadrant 2, the tan of alpha will be negative in quadrant 2. Now, quadrant 2 is defined by this here, okay? So because this has to be in quadrant 2, then this answer for tan of whatever this is has to be quadrant 2 as well. So tan of alpha is opposite over adjacent, which is -√7/3. So that answer for that one is negative. In this example, we're going to be using double angle results and the IDs that we used in the previous question to find the exact value of the following. So we've got the sine of sine to the -1 of 4/5 plus sine to the -1 of 12/13. So what we're going to do here is we're going to let alpha equal sine to the -1 of 4/5, and we're going to let beta equal sine to the -1 of 12/13. Therefore, sine of alpha is 4/5, and here sine of beta is 12/13. We will recognize these as Pythagorean triad. Sine of alpha, 4/5. Sine of beta is 12/13. We've got different angles here, so you can't let them both be alpha. This one will be alpha, that one will be beta. So we're working out the remaining sides using Pythagorean triads. 3, 4, 5. The other triad is 5, 12, 13. So therefore, trying to find that, we're going to say that's equal to sine of alpha plus beta, because we've let alpha be sine to the -1 of 4/5 and beta is sine to the -1 of 12/13. So therefore, sine of alpha plus beta, using our double angle result, is sine alpha cos beta plus cos alpha sine beta. Now with this one, we're fortunate that everything is in quadrant 1 because we've got a sine of something's positive and this cos of something is positive as well. And the reason we know it's quadrant 1 is because the inverse sine curve, remember that looks like y equals x cubed, we said, goes from, that's 1 and -1, goes from pi on 2 to -pi on 2. So even if you think, oh, wait a sec, it could be quadrant 2, well, it can't. Well, I know sine is positive in quadrant 2, but it can't be quadrant 2 because we have to go either quadrant 4 or quadrant 1, from -pi on 2 to 0 and from 0 to pi on 2. So it has to be quadrant 1 for both of these, okay? So sine of alpha, we already know what that is, it's 4/5. Cos of beta is 5/13 from this second triangle, plus cos of alpha is 3/5. And sine of beta we know already is 12/13. So therefore the answer to this denominator is 65. It's 20 plus 36 over 65, which is 56/65. With this one, using a double angle result again to evaluate the following. So evaluate the following with exact value, okay? So cos of 2 times cos to the -1 of 1/3. Now we're going to let alpha equal cos to the -1 of 1/3, which means that the cos of alpha is 1/3. So let's draw up a triangle. Cos of alpha is adjacent over hypotenuse, it's 1/3. So therefore the other opposite side will be the square root of 3 squared minus 1 squared, it's the square root of 8, which is 2√2. Okay, now we're trying to evaluate cos of 2 times cos to the minus 1 of 1/3, which is the same now as evaluating cos of 2 alpha, because we've let alpha equal cos to the minus 1 of 1/3. Now we can use any double angle result we want. Remember, we've got cos of 2 alpha could be 2 cos squared alpha minus 1. It could be cos squared alpha minus sine squared alpha is 1. No, minus sine squared alpha. So I could put 2 cos squared alpha minus 1, because I may as well use that one because I already know what cos alpha is. So that would be 2 times 1/3. See, cos squared alpha is cos of alpha squared minus 1. So 2 times 1/9 is 2/9 minus 1, which is -7/9. Now, I could have also gone with a different double angle result like 1 minus 2 sine squared alpha. Should get the same answer, which would be 1 minus 2 times, now sine squared alpha is 2√2 on 3, 2√2, sorry, on 3 squared. Sine alpha is 2√2 on 3, sine squared alpha is 2√2 on 3 all squared, which is 1 minus 2 times, that's 8. Actually, I should have kept it as √8, because then it's √8 squared is 8 over 9. So that's 1 minus 16 over 9, which is, as we got before, -7 over 9. Okay, because that's, and I could have also done it this other way, cos of 2 alpha, which is, but you wouldn't do it this way, cos squared alpha minus sine squared alpha, but it just shows, remember, there are 3 double angle results for cos of 2 alpha, or cos 2 theta. I could have used any of them. Cos squared alpha would be, we know cos alpha is 1/3, 1/3 squared minus sine squared alpha, this time I'll use the √8 on 3 squared. I should get the same result again. That's 1/9 minus 8/9, which we know is -7/9. So notice I'm getting the same result 3 times. It doesn't matter which of the double angle results I use for cos alpha. It just happens that there are 3 of them for that. With sine alpha, as we saw before, sine 2 alpha or sine alpha plus beta, there'll only be one double angle result for sine 2 alpha. There's only one double angle result for tan 2 alpha as well, so there'll be no confusion there. One final question. It says, if alpha equals tan to the minus 1 of 1/2 and beta equals tan to the minus 1 of 1/3, you have to show that tan of alpha plus beta equals 1. Okay, so remember, alpha is tan to the minus 1 of 1/2, which means that the tan of alpha is 1/2. Okay, beta equals tan to the minus 1 of 1/3, which means that the tan of beta is 1/3. Look, I'm not going to draw up any triangles yet because we may not need to use anything apart from tan ratios. We know that the tan of alpha plus beta from double angle, or from our sums and differences of angles results, is tan of alpha plus tan of beta over 1 minus tan of alpha times tan of beta. So there was no point here me drawing up a triangle and working out sine alpha, cos alpha, sine beta, cos beta, because I'm not going to use it for the tan expansion. Different when you're doing sine of the double angle, for example, or sine sums and differences, because the sine sums and differences has got sine and cos in it, so you would need both sine and cos. So here tan of alpha is 1/2, tan of beta is 1/3, over 1 minus 1/2 times 1/3. Now we can see that the denominator, easiest thing here to do, I mean, you can go common denominators if you want, okay. I like to multiply everything through by 6, okay? So I like to multiply because the lowest common denominator is 6, but look, we can go common denominators. 1/2 plus 1/3 we know is 5/6 divided by, for this, 1 minus 1/6 is 5/6, which is 1, okay? So that's 5/6 divided by 5/6, which is 1. So we've shown that tan of alpha plus beta is 1. Okay, now the next part of the question says, hence find the exact value of tan to the minus 1 of a half plus tan to the minus 1 of a third. Okay, now tan to the minus 1 of a half plus tan to the minus 1 of a third. Let's go back and look at our definitions. Tan to the minus 1 of a half is equal to alpha, and tan to the minus 1 of a third equals beta. So asking us to find the exact value of tan to the minus 1 of a half plus tan to the minus 1 of a third is asking us to find the value of alpha plus beta. Now we know that the tan of alpha plus beta from this part 1 up here is 1. So therefore, tan of what is 1? Therefore, alpha plus beta, we know that tan of 45 or tan of pi and 4 is 1. So tan of 45 or tan of pi and 4 is 1. Therefore, alpha plus beta is pi and 4. So therefore, just noticing as well, pi and 4 does fit into the domain that we're looking for. Therefore, we can say that tan to the minus 1 of a half plus tan to the minus 1 of a third is equal to pi on 4. What we're going to do, we're going to use similar techniques to what we just did to show that sine to the minus 1 of 1/5 plus sine to the minus 1 on root 5 plus sine to the minus 1 of 1 on root 10 equals pi and 4. Now what we're going to do, we're going to let alpha equal sine to the minus 1 of 1 on root 5 and beta equal sine to the minus 1 of 1 on root 10. Now we know therefore that the sine of alpha would be 1 on root 5 and that the sine of beta would be 1 on root 10. Now, so basically, if we've let alpha equal that and beta equal that, we're trying to find alpha plus beta. So what I'm going to need to do, I'm going to need to find the sine of alpha plus beta, okay? And I'm going to get a result for that. And once I've found that result, I'm going to be able to work out what alpha plus beta is, which is what that's really asking me to do. So I am going to have to find the sine of alpha plus beta, but in this case, we know that sine of alpha plus sine of alpha plus beta is sine of alpha cos beta plus cos alpha sine beta. So I am going to have to do up my triangles, right angle triangles. Now sine of alpha is 1 on root 5. So therefore this is the square root of root 5 squared, the square root of 5 squared minus 1 squared, which is the square root of 5 minus 1, which is the square root of 4, which is 2. So this remaining side here is 2. This is 1, and that's root 10. So this is the square root of the square root of the square root of 10 squared minus 1, which is the square root of 10 minus 1, which is the square root of 9, which is 3. So basically, sorry, I should draw it a bit clearer. That's my that triangle. And this triangle is 1 root 5, 2. Okay? So therefore, sine of alpha, I know, is 1 on root 5. Cos of beta is 3 on root 10. Plus cos of alpha, here's alpha, 2 on root 5. Sine of beta, I know from here, is 1 on root 10. So therefore, the sine of alpha plus beta is denominator's root 50, because it's root 5 times root 10 for both of them. And it's 3 plus 2, which is 5 on root 50. Now root 50 is root 25 times root 2, which is 5 over 5 root 2. 5 over 5 root 2, which is 1 on root 2. Now, if the sine of alpha plus beta is 1 on root 2, sine of what is 1 on root 2? It's sine 45, and 45 is pi on 4. Remembering we must be in the range of the inverse sine function, and that is pi on 4 is in the range of the inverse sine function. So therefore, sine to the minus 1 of 1 on root 5 plus sine to the minus 1 of 1 on root 10 is equal to pi on 4. Okay, I think that's it. We've done enough questions here.